Hello, this is a lecture of manufacturing automation, and this is the first lecture, Introduction to Automation. First, let's look at what kind of content will be covered in this lecture. The first, we'll talk a little bit about the basic elements of an automated system, and then I'll look at other than the major motion of automation, what other advanced functions can have in automation, as well as the level of automation in the manufacturing enterprise. And lastly, we're going to discuss a little bit how artificial intelligence and smart manufacturing plays in manufacturing. First, let's look at the history. The automation really started from a long time ago, starting from wheels, lever and screws and gears. Those are the little components. They are still called automation because there's a transfer of power, and so the power is also the basic element to generate motion. And then, in 1765, Watt created the steam engine, so that put, automation into another level. The same in that period, there's Matthew Bolton, created the flying ball governor. Also, so for this kind of automation, it start to have a feedback control, which means that the control will start to sense the status of the behavior of the motion from actuator. And then later, J-car loom was created, and this is this put automation into another level, which is the program instructions, which means that you can actually change the program and then tell the machine to do what kind of behaviors, right? So in J-car loom, then in the textile industry, you can create different patterns, of drawings or textile, and then the machine actually can, based on the controller or the operator's intention, and can choose different patterns to make. And then later in 1900, we all know that moving assembly line was created in the Ford company, and then all these car industries start to use mechanized transfer lines to move the car from the parts from one station to another. So this is and then started the mass production. And in 1945, people started to create this kind of computers. So computer really changed the automation, because it becomes more modernized with programmed language, and also the control, it changes from analog control to more of a digital control. And in the 1960s and in 1770s, digital computers started to connect to the machine tools, and now you can see more computers programs that are actually used in automation. And most recently, this is robotics, right? All right, so from this graph, you can tell that how automation actually plays in the manufacturing system. In the whole manufacturing system, there are many different functions. It has quality control, materials handling, identification, also some other supporting systems like finance, marketing, and administration, R&D, those kind of things. And the most basic ones are the manufacturing operation. And other than those, the automation also plays an important role in the manufacturing systems. So this is how manufacturing automation actually works with other functions to make this production happen in a manufacturing company. And the three basic elements of an automated system includes power, program instructions, and also control system. Okay. First, power. Power power sources, there can be different power sources. It can be electric power, fossil fuels, for example, all these vehicles, and also atomic solar power, hydraulic like water, and also wind power can also be used in production in automation. And general power forms, they can be thermal power or mechanical power, and also the light power. Thermal power will be more like, for example, in some of the manufacturing processes like casting or injection molding or welding, we can use the use the character that when materials at different temperature, they can actually behave differently. For example, some of the metals, when they have a lower temperature, then that is a solid state. When they have the heated temperature, then that will be in the liquid state. So that's the thermal power we can manipulate in order to form those materials into different shapes. And another one is the mechanical power. So mechanical power is used when when in some of the manufacturing processes like forging, machining, or punching, cutting, those kind of processes. It requires a mechanical or physical force from one material to another material in order to alter the shape of another material. So this is the mechanical power. Another one is the light power, because the light also contains energy. You can use that kind of energy to cut or to form shapes of other materials. And the power will be used in actually throughout the whole process of the manufacturing operation. It can be used in the loading and unloading of the part, transfer of the transport of the part from one operation to another operation, as well as the process itself. And the power is used into the control unit, and also to actuate the control signals, as well as collecting the data acquisition, for example, on the sensors. Another basic element is program instructions. So program instructions really is you tell machine what to do, right? You tell machine what to do. And there can be different categories. It can be set point control. So set point control means the process parameter value is constant during the work cycle. Means we set the parameter and the machine just do the same forever. With that setting. For example, a transfer line. Once we set the speed of say 1 meter per minute. Or 1 meter per second, whatever. Then the transfer line will always move at the same constant speed. Unless you tell the transfer line, you tell the control unit that stop or reduce the speed or doing what, then it will always keep that speed. So that's the set point control, which is also the simplest control program. Another type of control is the logic control. So logic control means we use logics to control the system. What does it mean? It means that for example, is a switch, right? A switch means when the switch is taking on certain values, then the machine will do different things. For example, when the switch is on the on status, then the machine will start to run. When the switch is on the off status, then the machine will stop. So this is a very simple logic. While another a little bit more complicated logic will be For example, in the transfer line, when we can use a sensor to detect, what type of the product it is. Say the color. If it is yellow color, it go to route 1. If it is a red color, it go to route 2. If it is blue color, it go to route 3. So this is also a logic control, and logic control can be programmed and used in the in the control language. It's called a programmable logic control, which is PLC. It uses a ladder logic to control those systems. Currently, PLC has been used a lot in manufacturing, and we're also going to discuss a little bit more in later this course. Another type of control is a sequence control. So sequence control means the value of the process parameter changes as a function of time. For example, timer, right? It can count for 5 minutes or 5 seconds. Then something will happen. Another 5 seconds, something will happen. Another 5 seconds, something will happen. So this is a sequence control. Interactive control program will be the machine's or the system's action is triggered by the human operator. So, for example, you can use a remote controller to control the height of lifting a product. Right, there's a grip. You can control that and go up and down to put in a certain place. So that's a very typical interactive program, because a human operator will tell the system what to do and to at what level. Another type is the intelligent program. So intelligent program, it will start to show some of the cognitive functions in the control. For example, it can make decisions, and it can also learn something from what happened in the production environment, and then will become its own knowledge. So next time when something happened again, it knows how to solve it. So these are the different types of the work cycle programs or program instructions. And now let's look at one example about it. So consider automated turning operation that generates a cone-shaped product. So the system is automated, and also robot loads and unloads the work unit. And the work cycle consists of the following steps. So these are the pictures about the operation of a turning operation. So the above picture is about it's a CNC turning machine with a robotic arm next to it, and the lower picture is about as a turning. What is the typical setup of a turning machine? So you know that where to hold the part, where the tools are held, and how it works. And you can also go to this link and then watch the video of what is a turning operation to understand a little bit more about this. Otherwise, it might be a little bit difficult for you to imagine or visualize the operation itself. Alright, so work cycle consists of the following steps. First, load starting workpiece, load the workpiece. The next one is to position the cutting tool prior to turning. And then the turn, and then reposition tool to a safe location at the end of the turning. And then unload finished workpiece. So these are the general steps, right? Now the question is, ask us to identify the activities and also process parameters for each step of the operation. So when we have those general steps, and these are not the language that the robotic arm and also the machine can understand. For example, if you tell the robotic arm, hey, just go and load the starting, load the workpiece. And unless the robotic arm is so smart, it contains all the programs already, right? Otherwise it won't recognize what you're talking about. And even though a very smart robotic arm, it includes a lot of details or complex information inside it in order to achieve that function. So now our job is to identify what are the specific steps or operations or activities within each step, and then what are the parameters are needed in order to finish that operation. For example, load starting workpiece. All right. If I say, "Hey, robotic arm, go to load it," robotic arm will not understand. But for a programmer, you need to tell, okay, robotic arm first, right? You move forward for a certain distance, and then lower your arm for a certain distance. Right? In this case, you create a 3D dimension axis, right? 3D dimension axis, and you know where is the point you are going to. So this is the first thing. You tell the robotic arm, and from one point to another point. And then next thing is you need to let the grip, right? Open the grip, and then close the grip and hold the part, right? And then lift it, right? So these are the detailed information or detailed operation programs that we need to tell the robotic arm what to do. And the question here in this example is to let us to identify what are these detailed activities, and also what process parameters are needed. For example, I need to know the distance, from the x-axis and the y-axis and the z-axis from the original robotic arm position to the place where the part is located, right? And then move from after the robotic arm's grip, hold it, and then want to move to another location, which is at the CNC machine. So these are the process parameters you need to identify. Now let's look at. So I suggest you think a little bit before you look at the solutions. The solutions is really a simple version of example to show it. And let's look at the first activity, which is the load starting workpiece. A robotic manipulator, first we need to reach the raw work part, right? And then lift and position the part into the trunk. Trunk jaw is the place where you hold the workpiece, right? And then retreat to a safe position to await unloading. So here we need to make sure that we understand that, right? After you load the parts, we still have the robotic arm there, right? We need to retreat it to a safe position, and then to start to wait for unloading. We cannot just leave the robotic arm in the CNC machine, there. And what kind of process parameters we'll need, right? Like I explained before, we need the axis values of robot manipulator, and also the part, right? And also the gripper value, so it is open or closed. We need to tell the gripper to open, and then close the gripper to hold the part, right? And then our trunk jaw values and open and close. These are all the CNC machine settings. Well, in the second operation, which is the position cutting tool prior to turning, the activity will be the cutting tool will move to a ready position, and then the process parameters will be access value of the tool to tell the tool where it should be moved to. It should move to, and then wait for operations. And the third operation will be the turning. So turning is the process itself, which is automated. But there are some of the process parameters we will need to set up. It includes the feed, the radial distance of the cutting tool, speed, those kind of parameters. And then in the fourth operation, that will be the reposition the tool to a safe location at the end of the turning. So when the turning operation finished, then you will have to retrieve the tool to its original location, to a safe location. And then after that, we'll have the robotic arm to unload the finished workpiece. In terms of what kind of process settings or process parameters we'll talk about, basically the same process parameter is just a reverse direction. Right. So from this, you can tell program instructions need to be very detailed in order to tell the machine or robot or control system of what to do. Right? They are not as smart as human. But even as human being ourselves, we probably do not recognize this information already processed in our brain. For example, if we want to reach, to get a bottle of water, right? First, in our brain already processed information of where that bottle is, right? So even this kind of simple operation, we need to tell the machine with a lot of detailed data. These are some of the examples that the programming instructions will involve some of the decision making. For example, it's a teller machine or a ATM, right? When you go to the ATM, it will ask you to have some of the choices, right? You can choose the language, right? English versus Spanish or some other languages, and then based on your choice, it will go to different route, right? You want to show all English or Spanish or some other language, and same, are you gonna do withdraw money or deposit money or just get some information? So these are decision making on the operator in interaction with. You need to choose, right? You need to choose those. Also, some of the decision will involve the sensor or the machine or the robotic, or the automated control system to recognize. For example, in this kind of a car production line, so this is the process when all the robotic arms need to weld the door of the cars. All right, so based on the model of the car, it is a 2-door car or it's a 4-door car, right? So first, the control system will need to recognize what model it is. Then it will trigger what kind of a program instruction it is, right? Because all the settings, all the distances, all the places where the welding position should be, are all different with 2 different models. So that's a decision that the control system can recognize by itself. So the different part or product styles processed by the system, and also some decision will be made at the starting work units, because we're gonna look at starting material. If there are is the original starting workpiece is too big, too small, and then based on that kind of information, the control system will determine, right, does it need another pass to machine it, or extra operations or longer operations based on the starting workpiece's dimensions or characters. So these are the decisions actually program instructions can make. Typical features of a work cycle programming include for example, number of steps of the work cycle, the manual participation in the work cycle that they require loading or unloading, process parameters, like how many must be controlled, and also operator interaction. Does the operator enter process data or not? And the variations in the part and part styles, and also variations in the workpiece, starting workpiece. And the next Next basic element of the automated system is the control system. So control system is more like the brain, right? It processes information and then gonna generate signal to trigger an action. And control system, typically there are two different kind of control systems. One is closed loop control, the other one is the open loop control. Let's first start with open loop control. So open loop control, you can see the lower part of this slide. Open loop control system it operates without feedback loop, which means it's very simple, and once we input the parameter, it will just go it forever, right? Without stop, unless you manually change the parameter or stop it, right? So this is open loop. And usually open loop is used in very simple and operations that does not requires a lot of feedback, does not require a lot of complex operations. Well, another type of control system is a closed loop control system. Closed loop control system, it has a feedback mechanism in it. So because there are some of the sensors that monitoring the status of the process. So when we see some of the processes are at a different status, then it will provide feedback to the control, and based on the feedback from the control will decide what to do next, right? For example, our heating system at home, right? When we set the temperature of 72 at home, when it will start to generate heat, when the home temperature is over 72, what happens, it will stop, right? And then when it's lower than 72, it will start to generate heat. So this is also a feedback loop. An example of the feedback or closed loop control is the lead screw driving system. So it's a very typical system because we see this a lot in CNC machines, in 3D printers, in a lot of other places that they involve the work table to be moved from one place to another. And it typically composed of controller, a motor, and also optical encoder. So and also a screw and a work table. So the optical encoder is the sensor that provides the information and also measures the distances between between the encoder and the work table. So when the work table moves, so the optical encoder will constantly provide feedback about measuring and the readings to the controller, and the controller will will decide does it want to move forward or move backward based on the optical encoder signal. So this is a very typical closed loop control system. And when do we use an open loop control system? And usually, those kind of systems should be used when the process is very simple, as I mentioned before, and also it's very reliable, right? Because it will not stop by itself. It will not change its value by itself. So if something happened, the machine itself can now detect it and then protect it by itself. So that's why when the open loop control system is used, we want to make sure that first the system is very reliable, and also the reacting force posing the action is small, so there's no bigger damage can be made to the machine or to the system. Otherwise, if something happened, it might cause bigger damage, right? Think about a CNC machine or mill, right? When you have a tool and then you tell the machine to go all the way down, and if there's no feedback, what happens? The tool actually is very hard, and then it's probably gonna damage the work table. Yeah, until maybe the power is off or something else. But if there's a sensor, or if there's a feedback, when we can set up a protection system that when the when the tool goes down to a certain level, it will automatically stop, right? Or emergency power will automatically shut. So this is a feedback system. And open loop control system, if you do not have feedback, you want to make sure that that kind of impact or forces is really small, so it will not cause too much damage. If these conditions do not apply, it's better to use a closed loop control system. And a form of different now, because we were starting to use computer process control. We all process the computers, and now let's look at different types of the controls. So analog control versus a digital control. Analog usually deals with signals that is continuous, while digital controls usually deal with signals that is discrete. Right. So continuous control means within a certain say a gap or a segment of the two values, right? There are unlimited numbers in it, right? Well, in a digital signal means that within certain two values, there are only two values. For example, 0, 1, either 0 or 1. But analog signal, between 0 to 1, there can be unlimited values. So the variable can take any kind of value, like 0.01, 0.001, 0.001. These are two different type of the signals we have. And later we're going to talk a little bit more about what is digital control and how digital control works in further lectures. And another type of control is computer numeral control. Another name is CNC. We already heard in production. So CNC is a computer-directed machine tool that can conduct those machining operations with program directions. So program directions were made by the human being. So we can program those in a CAM software. Then the software will generate a certain code to tell the CNC machine what to do, where to do. For example, like tell the machine to move from here and there, and also at what time. So this is a CNC machine. Another one is the industrial robotics. So industrial robotics is different with CNC control. It is made of manipulator joints, right? With different joints, it can actually move with more movement space compared to CNC. And they can conduct a sequence of positions in a work cycle. So PLC is also one type of computer process control. We'll talk a little bit about PLC. It's a program logic control, and it executes program instructions to implement logic, sequencing, counting, and also other functions to control the industrial machines and processes. It was first introduced in around 1970s to replace the relays controllers. And today, PLC can be used in both discrete and continuous control in both process industry and also discrete product industries. So later we're going to talk more about PLC. And also we have one type of control, it's called supervisory control. So supervisory control is mostly related. It's used in the process industries. Process industries means mostly they are continuous processes. For example, in chemical processes, right? We are dealing with liquid. We are dealing with certain temperatures. Maintaining the status of the liquid, and like also gasoline, right? Those and so the supervisor control is when we are controlling the systems, we are looking at different parameters now, and then want to make sure that integration of those parameters actually we're going to achieve a certain economic objective. So we want to make sure they are with the lowest cost we can make the maximum output. Well, in discrete manufacturing, supervisor control is a control system that directs and coordinates the activities of several interacting pieces of the equipment. For example, scheduling of the production, right? We can have a human being actually working with computers to control that. There's a supervisor control to see if where the product is at right now, on the production line. And then to trigger some decisions on what to do next, right? How if something needs to be changed or not. Also, human, or computer systems can start to use some algorithms to optimize the operating parameters to achieve a certain goal. So that's a supervisory control. More of that at a higher level to make sure all the whole processes, activities are working well. So this is the diagram we're looking at of this supervisory control, and so basically the process, and also we have input parameters, output parameters, and this is the feedback system. Like going back to this is the controller. And also controller will make decisions and then trigger the input parameters change and then to control the system. Well, on that, the supervisory control will actually add on that is we have this control system that based on the decision of a human interface. Right, we can make decisions to make sure that this controller is working towards the way that we want. Right, so this is a supervisory control system. There's another control system. It's called a distributed control system. You can tell from this graph. So this distributed control system, these are means that multiple microcomputers are connected together to share and distribute the process control workload. When we have multiple processes, a lot of workstations, like 1, 2, 3, 4, and more, right? And we cannot just only use one computer and then process, always control everything all at the same time. Then it will gonna cause a lot of workload for a single computer, and also it's gonna also created a little bit of errors as well. In this case, people started a distributed control system, which means that we have each one will have a control unit, right? Each one will have a control unit, and then all these control units will be connected through a network, right? And then to make sure how everything works better. Then we have a central computer to control all the other microcomputers. And this is the distributed control system. Advantages of the distributed control system is that it can be installed in the very basic configuration. Then it can be expanded, right? When we add more processes, we can add more computers and just connect it to the existing network. And also, multiple computers can facilitate parallel multitasking. The network also provides process information throughout the enterprise for more efficient plant and process management. So this is the enterprise-wide integration of the factory data. So when we are looking at the automation and also the control systems, we are not only looking at the one single machine itself. Actually, those data can be and aggregated into at the shop floor level, and then to control the whole production, and then that information can be also kind of aggregated to enterprise level. So look at how the production, overall production works, and then how can we use production planning strategies to change or optimize the operations at the lower levels. So really there are different levels of a control system. It's more like our university system, right? We have medicine have many different functions, right? Finance, or so, academia, or also some other safety, those kind of things. While within each of the functions, there are also some lower levels, like we have departments, and then we have different courses and the different classes, right? So this is all the information that can be aggregated and integration to for better use of the data to achieve the function. And so other than about automation, other than the main function, which is the movement of the process itself, there are also some other functions. We call it advanced automation functions. Include safety monitoring, maintenance and repair diagnostics, and also error detection and recovery. For example, safety monitoring, we can use sensors to track the system's operation and also identify some conditions that are unsafe or potentially unsafe. A very simple example will be our garage door, right? We have this infrared beam at the bottom of the garage door. When someone walks down there, and then it will automatically close or stop movement of the garage door. So this is a protection. We see that. Well, the similar protection we can see in the production environment. For example, we can put that kind of beam at the next to the machine. If it is that is a little bit dangerous environment, then we do not, when the machine is working on the process, we do not want any human being to enter that environment and then probably suffer from any kind of a potential hazard. So that kind of safety can be implemented there. And also there are imaging monitoring that can also be used for detecting potential unsafe environments. And when we are talking about the safety, it's not only just about human safety but also the equipment safety, right? Because when like I explained before, about this kind of a cutting machine or the CNC machine. If the tool is going too far, then it's gonna damage the machine itself, right? So we can start to implement some of the safety functions or monitoring or sensors to provide the feedback to the control system so that it can detect any potential unsafety environments and then quickly either stop the stop the process or create a different responses like sound alarm, or reduce the speed, or some other corrective actions. And also another function we can achieve with automation is the maintenance and repair diagnostics. Maintenance, we know that it mainly that's the status monitoring, right? The very very simple one will be the the gas tank gauge, right? Indicator. We can see what level of gas we have in our tank. And so it monitors some of the key parameters of the system, so if you need some more maintenance for the system. And also it can diagnose some of the failures, see why it happened, and what kind of repair procedure they should go through. A typical one will be the we often see in our computer, Windows operation system. When something happened, they're gonna say, okay, check this and check that. and then will automatically check one another, and then will detect, okay, what is the problem with that, and then will give you some of the suggestions on how to solve it, right? So same with automation system in production. And it can also detect some of the errors and also create some of the recovery mechanisms in the system. For example, in our vehicles, right, we have this check engine light. When it is on, then you already go to the car shop, and then car shop will use that kind of a reader, right, to read the code. So because when the light engine is on, usually it generates a code. So that code is something that the control system can recognize or detects, or where is this wrong in the machine, right? And then with that code, the car shop operator, car shop employee can figure out, okay, what is wrong with your car, and then to fix it. And in terms of error recovery, possible strategies can be make some adjustment at the end of the work cycle. So after work cycle is done, we can make adjustments, or we can just make adjustment during the work cycle. For example, when we see the cutting temperature is too high, we probably want to reduce the cutting speed to lower the temperature. In this case, we do not actually stop it or wait until it's done. Or in some of the cases, we just stop everything, right? All right, so let's look at another example. So consider an automated cell consisting of a numerical control machine tool, a part storage unit, a robot for loading and unloading the parts between the machine and the storage unit. So possible errors that might affect this can be divided into the following categories, right? Machine and process. So think about what kind of possible errors, right, can happen to machine and process. For the cutting tool, what kind of possible errors can happen to that? Same with work coding fixture, part storage unit, and also load and unload robot. What kind of possible errors can happen to that? So when you are designing automation system, or working with the control system, you need to figure out, or can foresee the potential reasons that it can cause malfunctions, right? So this is the one exercise you can use to exercise the error detection and recovery. For example, for the machine and the process, either maybe it's loss of power, right? Or the power is overloaded, right? Or thermal deflection, or the cutting temperature is too high. Maybe there's the operation, vibration, and of the machine tool, right? And there's no coolant, chip falling, wrong part program, defective part. These all can go wrong with the machine and the process. Well, for a cutting tool, maybe the tool broke, right? And all the tool ran out, or there's too much variation of the tool itself, or maybe there's no tool at all, right? Or it's the wrong tool. And same with the whole work coding fixture. Some of the errors can happen in when there's the part is not in the fixture, the clamps not actuated, part dislodged during the machining, part deflecting during the machining, or part breakage, chip causing location problems. Also, you can look at some other two type of two components of the system, like part storage unit, what can go wrong, and also load and unload robot, what can go wrong. And this is another exercise when we detected the problem. So how can we save it, right? What should we do, right, in order to address those errors? For example, if the chatter or too much tool vibration, maybe because that is the cutting speed is too high, then we can reduce the cutting speed to change the harmonic frequency a little bit. And if it's cutting temperature is too high, then we're going to reduce cutting speed. If it's cutting tool field, then we just replace replace the cutting tool, right? Or if there's no more parts in part storage, then when the call operators to resupply the parts and also same with the chip, we can clear the chips from the work area. So two major functions in this, and one is error detection, right? Know what is wrong, and also know what to do, right? Know what to do for the automation. So it all need to be programmed in the control unit. So you can give hints or give suggestions to the operators or to the control system on how to solve it, how to solve the problems. Next, let's look at the levels of automation. Just like I explained before, the level of automation really happens at all levels, starting from a single device, right? Single device like a robotic arm, right? To the whole work cell, right? To whole work cell. And then go to the plant level, which is a series of manufacturing processes, right, composed of whole production system. And then going upper, we have this ERP system where it incorporates all the information from many different functions, finance, marketing, R&D, blah blah those, and so that make the automation really at happen at all levels. And the last thing, I'm going to talk a little bit about artificial intelligence that is used in automation, because there's a really popular topic right now, and I believe it is also the trend for future manufacturing control systems. And artificial intelligence mainly it means that the computer system or the control system are starting to use some to have some cognitive capabilities, like perceiving, learning, right, reasoning, and remembering and something, making decisions, those kind of functions. And the areas application of AI includes in manufacturing automation involve these are more the general functions, right? Problem solving, game playing, natural language in communication, analyzing large amount of data information, planning out, strategizing, drawing inferences from incomplete data. While in manufacturing, it can actually be implemented into a lot of functions as well. For example, in the process control, in advanced functions like we discussed before, like safety, detecting errors, or everything. All right. So in AI, there's a term is called expert system. So expert system is actually composed of different components. So one is the computer's programs that when they contain a technical knowledge of experts in a given field, we call it the knowledge base. So knowledge base means it's a database that includes all the information that is exists, right, to for the control. Or basically, in a simple word, it will be what does computer know so far, right? What does the computer know so far? And it includes some general facts, some principles, logics, procedures we already programmed, and all the rules. Some of the rules we programmed into the control itself. So this is knowledge base, but it does not make the computers too smart. What makes the computer smart is it can use algorithm to apply those knowledge to a specific problem, right? We have this. We programmed the algorithms, and when a new problem happened, what happens is the computer control system actually can use those knowledge base to solve the problem that happened in the action in the actual process. So we call it data inference engine. So applies knowledge base to a fact to a new problem in the application field. And so data mining. So data mining is it's actually it's a computation process. Basically, it's to review or unveil some of the patterns or phenomena that is hidden in the data. So what it means is, when for example, in our social network, okay, people are searching many kind of keywords, right? At a certain time, maybe before election, after election, before New Year, after New Year, before Christmas, after Christmas. We can see at different times people what people are searching, and then with data mining, we can actually people can generate some of the keywords that is most searched in during a certain time, and then based on that keywords, we know what's on people's mind, right? What some people either for shopping or doing something else. So these are the patterns that can be unveiled, from the data, right? From the data, and people now you are using those kind of informations to generate a lot of marketing ideas, and then do a lot of different things. So this is something we can do with the data mining. Same with manufacturing, right? When we have a lot of data that are collected on the process, right? For example, we measuring the dimensions of the part, then we can see what the variation of the part quality of the dimensions. To see maybe after a while, say after 2 or 3 days, the tool, machine tool will create some of the chatters, will create some of the bad parts. Then we can use this kind of information to tell the operator that we're gonna create the mechanism that we're gonna change the tool every 2 or 3 days, right? So these are something that data mining actually can help us to improve our processes. Well, machine learning is also is a new tool we are using a lot in manufacturing as well, especially in the future. And so basically, it's a computer algorithm that that are able to learn on their own without being taught explicitly, right? In traditional computer controls, we need to program all these logic, all these algorithms into it without let them know. But when there is a new thing, right? When there's new phenomenon that happened, usually the machine does not know what to do because it does not provide the feedback loop to the knowledge base. Well, the machine learning actually creates this kind of feedback that it will learn from the new phenomenon or new problem, a new knowledge, and then enlarge or build that knowledge into its knowledge base. So expand its knowledge base. So there are several ways the machine learning can occur. One is the supervised learning. So supervised learning means we create a sample, right? We create a sample of the problem, and then our example of the problem. And when the machine or when the computer or when the control system recognize a similar problem, not exactly the same, so they can actually use the examples, and learn from the example, and then to solve the new problem. So the supervised learning. And in reinforced learning will be the computer receive the positive and negative feedback as it attempts to learn from observations. So it's the computer will learn what to do, or it is right or wrong, based on the behavior it did. For example, when the computer, the control system reaches, to the left, then, for problem solving, then probably it will, it detects that something will create certain potential hazard. Then it will mean that's a wrong, the negative feedback. So they learn that, okay, I cannot reach it to the left. I need to go to the right. So this is kind of reinforced learning. And the next one is the unsupervised learning. Basically, it's a computer is left with its own devices to find structures and knowledge to enlarge its observations knowledge base. That is more smart and without creating without giving any examples, giving any original feedbacks. So the computer can actually learn it by itself. It's more like in this course, for example, if I give you an example and of the problem, then in the exam I will give a similar problem. Maybe I only change the numbers. Then that will be supervised learning, right? Well, if I give you an example in the lecture and then in the exam I give you another type of the problem, but ask you to explore a new method, right? Ask you to explore a new method. So you can use a new method to find out if you got a right or wrong answer. If the answer matches what is needed, what is supposed to be, then that means your new method works. If it does not work, means that is that's that means if it gives a negative feedback, means that's your new method does not work. So this is reinforced learning. Well, unsupervised learning will be like I give you an example on a type of problem. I could totally give you a different problem, but the problem is also related to a. It just we're gonna use a totally different method, totally different problem, but it's the same kind of knowledge, same kind of nature problem you're going to solve. So this is a diagram that shows how the machine learning actually works in artificial intelligence in the intellectual process. The reasoning power, that is the logic, and how the algorithms, and also the control unit, how the speed of that. And the knowledge base will be, the original knowledge or the database of what is known in the computer control system. And our computer control system will generate the algorithm to solve the problem. When there's new problems, then it will provide feedback to the algorithm and also feedback to the knowledge. So it creates a feedback. That kind of feedback information will enlarge or expand the knowledge base. So this is how we just start to build stronger and stronger knowledge base by itself. With this AI. Some of the applications in manufacturing model AI include computer-aided process planning. For example, maybe in the future, when we have one product, a shape, material, right? There it can automatically program everything for you in the machine. You just need to load the part, and that's it. So that originally, what people are doing right now is we need to manually to input all the parameters, right? Input all the designs in the computer-aided software to generate the program. And a lot of times there can be errors, a lot of times it can be problems, but maybe in the future the AI can help us to, by identifying the material and also the shape, it can automatically generate those kind of planning of the processes. And same with CNC part programming and also robot programming, robot interacting with humans. They can also be very smart based on what human, for example, the language communication, or by detecting how the human are moving from here there, and they're gonna interact with that. Same with production planning and control. We can look at the scheduling, forecasting. A lot of those can use AI or machine learning algorithm to help us improve the performance. Same with diagnose of the machine malfunctions, and also to program the autonomous material transport vehicles. Yeah, in some of the very big, large, warehouse in Amazon, they already have those kind of starting to use those, automated routing system for transporting people's packages. And so lastly, just a little bit about a smart manufacturing concept and also Industry 4.0. This is really about digitalizing and also making everything so automation with smart decisions, and also cognitive decisions can be made with machine systems by itself. And so that's, with all this information transferring, information manipulating, it comes up with this whole Industrial 4.0 or smart manufacturing concept, right? That is compared to mass production, and also the automation that is happening in before 2010 or before 2000. So that's a total. We are entering into a totally different era of the of manufacturing. All right, so yeah, basically the same concept. We're dealing with more of the data in manufacturing right now. Using a lot of more of industrial Internet of Things in factories. In fact, a lot of those new technologies come from manufacturing. Right? Think about all these production lines in the food industry, in service functions, like if you go to Subway, right? The Subway has this production line where making sandwiches. They actually learn from production, right? And all these AI, automated system that we can see, or robotic system we can see in our lives, actually they are being used or have already been used a long time in manufacturing. For example, AGVs, right? AGVs can actually automatically detect the route from here and there and then carry things. Now you can see there are some kind of robot that can carry. Can deliver food, right, on our campus. They deliver food from restaurant to our place. It's kind of the same concept. They just move from the factory to our lives. All right, so these are some of the takeaways from this lecture. Mainly about basic elements of an automated system, some other functions, advanced automation functions, safety, maintenance, error detection, and also level of automation, right? And also how the artificial intelligence, machine learning, data mining, those kind of technologies are used in automation right now and also in the future of manufacturing. That's all for today.